Dear student, in our earlier video, we have studied ideal gas equation. Now in the present video, we'll try to study pressure of an ideal gas. Let us study assumptions of kinetic theory of gases. Molecules are rigid spherical in shape. Volume of molecule is much smaller than the volume of the container in which it is kept. There is no intermolecular force of attraction. Collisions between the molecules and the wall of the container are elastic. Molecules have different speed, so they have got different kinetic energy. The average kinetic energy is directly proportional to the absolute temperature. Let us start deriving the expression for pressure exerted by the ideal gas. Consider n moles of an ideal gas enclosed into a cubical box of length L. As we have seen in earlier slide, molecules are in random motion. So consider the molecules which is traveling along x-axis. So its velocity component along x-axis is given by Vx. As the collision is an elastic, what happens is only the direction is reversed. The magnitude of the velocity remains the same. So change in momentum is given by final momentum minus initial momentum, that is minus 2m Vx. Now the average force is nothing but the average rate of change of momentum. For that you need to calculate what is change in momentum, which we have already calculated, divided by the time. To find out the time, the total distance traveled divided by the speed, so that we have calculated as 2L upon Vx. So the average force will be equal to mvx1 square divided by L. Here Vx1 is the x component of the velocity of molecule 1. Now in the similar manner, we have got n number of molecules with their x component given by Vx2, Vx3, Vx4 up to Vxn. The total force exerted on the wall is given by m divided by L in bracket Vx1 square plus Vx2 square plus Vx3 square up to Vxn square. The average pressure will be average force divided by the area of the shaded wall, which is nothing but m Vx1 square plus Vx2 square plus Vx3 square up to Vxn square divided by L cube, as it is seen in the slide. The average of the squares of the x component of velocities is given by sum of the squares of the x component of the velocity divided by the number of molecules. So thus we get pressure P as mn v bar square x divided by v, as we have studied last year. According to the resolution of vector, v bar square is equal to v square x bar plus v square y bar plus v square z bar, and as there is no preferential direction for motion of the molecules, all the components will have equal possibility. Thus we can write down v bar square x plus v bar square x, which is equal to v bar square y, which is equal to 1 by 3 v square bar. Thus we get pressure P is equal to 1 by 3 n divided by v into m v bar square. Thus we get v bar square as 3nRT divided by Na, that is Avogadro's number, into number of molecules into mass of the molecule. In the resultant we get the square root of the average square of the component of velocity as Vrms, which is equal to square root of 3RT divided by m. In the inset you observe the graph which shows how does the speed of the molecule varies with the number of molecules, which is called as Maxwell's distribution of velocities. Now let us try to interpret kinetic energy of the gas in terms of temperature of the gas. In our earlier derivation, we have studied pressure P is equal to 1 by 3 n m v bar square divided by v. I can write down the same equation as PV is equal to 1 by 3 n m v bar square. Now rearranging the same equation, we can write down 2 by 3 n in bracket 1 by 2 m v bar square. Now the bracketed term is nothing but the average kinetic energy. Now the same equation can be written as 3 by 2 n kb into T, or I can write down the average kinetic energy per kilomole as 3 by 2 R into T. Now let us try to find out RMS speed of oxygen at NTP. RMS speed of oxygen is given by Vrms, which is equal to square root of 3RT divided by m, which we have already studied. Now if I substitute the data in the given equation, I get Vrms for oxygen at NTP as 461 meter per second. Similarly, you can calculate the RMS speed of nitrogen and hydrogen, as well as we can calculate what is the RMS speed of the gas at any higher temperature, as shown below.